So now, without further ado, I'm very pleased to introduce our keynote speaker, Dr. Stephen Hauser. Dr. Hauser and I were at a meeting which seems like ages ago, and I knew that we were interested in having Dr. Hauser come and present to us today about the new things on the horizon. Little did we know there would be so much new that's on the horizon. And he just kind of looked at me like vaguely, like, you want me to do something a year from now? And I said, yeah, I do. And he said, oh, sure, okay, I'll do it. And then obviously as time goes on and more information becomes available, he's had to whittle all of this down, and I'm sure he will do a wonderful presentation for us. He's an internationally renowned neuroimmunologist and certainly a distinguished professor at the Department of Neurology, and he's also the chair at the University of California in San Francisco. He's had some groundbreaking work in the role of genetics in multiple sclerosis, and I know that often in my practice I get asked about things like genetics and heredity and various different ways of how someone might actually develop MS, so I'm sure we're looking forward to that. He's also helped many to better understand what may trigger the disease in individuals and families. And as John mentioned earlier, he's the winner of the 2008 National Multiple Sclerosis Society American Academy of Neurology John Distal Prize for Excellence. So please join me in welcoming Dr. Stephen Hauser.
Thank you, Amy. So my mic is working, I see. Can you all hear me? Great. I tend to roam around, so I will hopefully be audible and mic'd throughout. Now, I'm going to try to do a little bit of a high-tech presentation. My kids would be stunned if they thought I was actually going to try this, but I may go between a number of different computers as we're working. So let me just hook this up and see if the magic works. How are we doing? So. Bingo. Well, as Amy said, when I was asked to speak, my first thought was, I will do anything for the National MS Society. I had been here before speaking about genetics, I believe about 9 or 10 years ago. Do any of you remember back that far? Yeah, so as Amy says, so much has happened. And what I'd like to do this morning is to tell you a little bit about genetics, a little bit about where we are headed in terms of developing better therapies and really understanding how to make sense of all these magnificent therapies that we have developed, where I think we need to be in order to have that cure that we heard about be reality. Yesterday I was asked how close we were, and I think we're about 1/3 of the way there. We know a lot about the inflammation. We're beginning to understand this terrible problem of progression. And repair is a great, great challenge, but also a problem that we are now beginning to break through. So I think that the prospects are incredibly bright, and that is the take-home, one of my take-home messages. The second take-home message is that everything I'm going to tell you, and likely anything you will hear from any other speakers, would never have been possible without the ongoing agenda setting, advocacy, and funding by the National MS Society that has made all this possible. And if I forget along the way to tell you how the MS Society has enabled this work, that is just my forgetfulness and not any lack of recognition for the society, because it has been absolutely instrumental. I was warned in an email earlier this week that the talks that physicians give are too simple, that the audience is really deep in their understanding of science, and I should make this really tough and unpleasant. So, if it isn't as entertaining as you hope, I'd like you to do as they did in that episode of Seinfeld. If you could just tap your head, I will make it more fun as we go along. But I hope by the end I can show you a little bit of a vision for where we need to go. And I'll make sure that we have time to do that. I'd also want to thank everybody for coming. It's just such a beautiful Saturday morning. We don't get these crisp mornings in the Bay Area, so I know it means a lot to get up early on a Saturday and come out to the airport, so I'm very appreciative. We know that MS tends to run in families. It runs in families in all ethnic groups. When I was here 9 years ago, I left a message that maybe we could actually find exactly why MS runs in families. We know that it's not all inheritance, that it's in part inheritance and in part environment. For some of us, it's more inherited, and for others, it's more environment. But for all of us, it's a little bit more environment than inherited. So for those of you who have children, my message is, do not worry about your children. Worry about your children, but don't worry about MS. With the single exception of those very rare families who have been so important for the genetic studies, where there are 15 or even 25 people with multiple sclerosis. If you don't belong to a family with very, very large numbers, you don't need to worry about your children. Worry about sports accidents. That's the kind of thing that is just so much more a problem than the children actually developing this problem. Well, we're a very young species. We're only 180,000 years old. Evolutionarily, this means that we're not very different. There just hasn't been enough time in the 7,000 generations since Adam and Eve for us to have enough mutations to make us very different. So we are all more than 99% identical. That's really interesting. We are all very much more alike than we think. But that less than 1% is responsible for so many of the differences between us. Why some of us are tall and some of us are uncomfortable speaking in public, and why some of us have a better jump shot than others. It's also important to know that in the history of human evolution, there was a genetic bottleneck about 70,000 years ago during the most recent migration out of Africa, where our ancestors all come from. And because of that, a very small amount of the genetic diversity in the human population got out to populate first Asia and then Europe. So there is more genetic diversity in a single African village than there is in the rest of the world together. Very interesting and very important for genetic studies. And the genetic studies that have been done have focused both on the European as well as these very important African genetic contributions to multiple sclerosis risk. Now, it's very important to remember that despite the urbanization in Africa, MS is almost unknown, even in the big cities in Africa. And yet African Americans have a high risk for multiple sclerosis, and we know that when African Americans develop MS, they tend to have, in some cases, a more severe course, and we've been able to identify the genetic basis for that. There was a remarkable study that I spoke about last night by friends in Buenos Aires. They were studying people with multiple sclerosis by MRI, longitudinally, meaning over time, and all of a sudden, they stopped developing attacks. The MRIs became silent, people felt better, they were not having attacks. And a SWAT team went in to figure out what had happened. And they had been infected in their home communities with intestinal tapeworms called strongyloides. And this turned off MS disease activity. And we know in terms of the immunology how it turns it off. These worms create an immune environment that stops inflammation. And this gets to the question of environment and how complex the relationship with environment and genetics is. So one could have all the genetic background, but with a good environmental exposure or a bad environmental exposure, a problem may never materialize or may materialize. So remember that environment is very important. The beauty of genetics is that we can use genetics to identify risk without making any assumptions about what the cause of the disease is. So we can say, let's just let the genetics tell us what the cause of MS is. And that was the dream 9 years ago. And thanks to the integral support of the National MS Society, we were able to bring together first investigators from around the United States and then a global group of investigators, the International Multiple Sclerosis Genetics Consortium. If I showed you the picture, there are hundreds of people posing for a photo from all over the world. 35,000 patients and real answers. And in the next few minutes, I'm going to show you the real answers, and then at the end, begin to show you how these answers can help us shape advice to individual people. So what are genes? Genes are modules of information. Everything that our body does is influenced by genes that make proteins, that do things in our cells. Every gene is in every cell except for platelets, this clotting cell. Genes are polymorphic. That's a science term. I'm only telling you this because Colette demanded that I get very technical. We'll have Chicago medical licenses for those of you who follow all of this. So what polymorphic means is that they come in different flavors. The building blocks are a little bit different. But remember, less than 1% different. They're 99.7% the same in all of us, except for our sex chromosomes. Women are different than men. We have a little over 3 billion building blocks, which are our DNA, right? 3 billion. We actually have double that because we have 2 copies of every building block. Each of us has about 10 million differences that distinguish us from everyone else. Those are our inherited attributes. Very interestingly, I'll tell you in a moment, we guessed, just doing mathematics, that between 50 and 100 of these 10 million lead to MS. In 2012, we now have 62. We were so close. It makes you believe in science. And if any of you have Tea Party friends, you can speak to them about that. We have actually about 23,000 genes and change, but 25,000 to round it out. A gene is a number of building blocks, usually about 1,000. It's broken up into pieces, but it turns into a protein through RNA. So DNA makes RNA that makes a protein that does something in a cell. We have 23,000 genes. I'm sorry. And they are on 23 pairs of chromosomes, 22 autosomal pairs, and then the sex chromosome pair. What's really amazing is that mice have 23 chromosomes, 3 billion building blocks, 25,000 genes, and each gene is about 1,000 building blocks. Isn't that amazing? Obviously, the differences in the DNA, which is identical in human and mice, this 0.7% that makes us all different, the differences are really significant. So what was our challenge? Let's find the differences in flavor that make people susceptible to multiple sclerosis. And as it turned out, that was a harder task than we had anticipated. The first studies were in 1996, the second studies in 2005, and then thanks to new technologies, last year the final roadmap of MS genetics was finally published by the International Consortium. This was just a wonderful achievement. The genes at this time are all related to risk. What makes us inherently at risk for multiple sclerosis? The next step, there's always a next step. The next step will be to find the genes that cause progression. And we are gearing up to do that, hopefully with widespread multinational support over the next few years. So I'd like to show you in a few-second movie exactly what the genetic story has taught us. And Colleen, I promise this will be complicated. So let me show you. Here in this circle are 4,000 little dots that are 4,000 genes, okay? In the middle. Can you see that? Right here, okay? Here are 1,000 human diseases for which we now have genetic studies. And here are drugs. So this is on your left. The circle here are FDA, Food and Drug Administration approved drugs, of which there are about 3,000. Okay? Now, do you see all those wires? The wires are showing how the diseases on your left connect with the genes and how the drugs connect with the genes. And where is multiple sclerosis? Well, I'm sure you can all read it, but multiple sclerosis is right here. It's a green one. We're now going to use mathematics to analyze terabytes, many, many terabytes of data, more than can imagine. To bring the diseases and the genes and the drugs together so that you can see the relationships and what the fruit of the MS genetics effort has taught us. And this is just a summary, and we can speak about some of the depth later on. But what I'm going to do now is activate the cartoon so that you can see the diseases and the genes and the drugs come together. Ready? So, they're sorting based on their mathematical relationships. They're coming forward. The diseases are around. Multiple sclerosis is in the center. There are the genes, and there are the drugs. And it gives us relationships that were inobvious, that wasn't obvious. MS is in the center. What is related to multiple sclerosis? Psoriasis, lupus, rheumatoid arthritis, inflammatory bowel disease. No neurologic diseases. They're all the way off on the other side. Alzheimer and Parkinson and Lou Gehrig's disease. MS is an immune-mediated disease, at least in terms of risk. The genetic background of people at risk for MS also is shared by the genetic background at risk for people at risk for other inflammations. And we see this most clearly in people who have MS and who also have someone else in their family with MS. So if you look at people with MS in general, more than 5% of people have psoriasis also. And if you have MS in your family, you are very likely to have relatives with one of these other problems. So this tells us that the fundamental driver of risk for MS as it's inherited is not a problem in the brain. It's a problem in our inflammation system, in our immune system. This is very important. And it also gives us magnificent opportunities to look at drugs that counter some of these genes or are effective in some of these other conditions, and then to tailor the use of those drugs for individual people who have that specific genetic change. These are not mutations. These are not bad mutations. These are just variants, polymorphisms that are very common in the population. For example, the third MS gene that we found, which is my favorite one, because my wife, who's a hematologist, had cloned this gene in the 1970s. And she then quit molecular biology because she said this gene wasn't interesting. Well, 30 years later, it turns out to be an MS risk gene, and people now all around the world are interested in studying this gene. Well, this gene is carried, the flavor of this gene is carried by about 85% of people with MS. But it's carried by 73% of people without MS. So you can see that these aren't bad genes. Some of them are very common in the population, but they do increase the risk for MS. And certainly these variants were selected during evolution because they did something good. They might fight infection more actively or fight cancer more effectively. But the downside is that in the right environmental situation, they can create a misreading of some infection, presumably, that looks to that overactive immune system like myelin. So we want an active immune system if we have an infection, but we also want that immune system to behave and not to attack our own tissues. So nobody is tapping their head, is that right? Okay. So we haven't yet found any genes. Well, let me say one more thing about the genes. Almost all of them are genes that are involved in inflammation. But two of them are a little bit different, and they're very exciting. These are the two genes responsible for the synthesis and the degradation, for building and breaking up the active form of vitamin D. And we know from studies of populations that vitamin D deficiency is very prevalent across northern societies. In the United States, 93% of us are vitamin D deficient. We don't eat enough deep sea fish. We use sunscreen. We get most of our vitamin D from sun. We get some from fish. We haven't until recently taken supplements. So the vitamin D story is so important because vitamin D is a regulator of this critical cell called a macrophage, or a microglial cell, that we think is a bad actor in multiple sclerosis. Vitamin D turns that cell down. And this is probably one of the reasons why people with MS may tend to be especially vitamin D deficient, and why vitamin D deficiency is a risk factor not only for developing MS, but maybe for MS behaving worse after it starts. So everybody, I think, should be supplemented with vitamin D unless our levels are 50 or 60. So I think vitamin D replenishment is an important lesson that is emphasized from the genetic work. I'm going to speak for a moment about myelination. This is critical to repair. There are two types of cells that are making myelin. One is called a Schwann cell. It makes myelin in our peripheral nerves, in our arms and legs and to our gut. The other is the oligodendrocyte that makes myelin, of course, in the central nervous system. And as you all know, myelin wraps around nerve cells, protects them, and expands their life. And we think that when there are MS scars or plaques, the lifespan of the nerve cell that sends its axon that goes through the scar is shortened. And that's why an attack in 2012 can contribute to progressive symptoms in 2032. And that's why, if we can protect against attacks at the beginning, we are very confident that the risk for progression will be limited down the road. That's a very important principle and a great accomplishment. It means that treating early and treating completely so that there are no new lesions can be very effective over the long term. The myelin in the peripheral nervous system and the brain is almost identical, but there are differences in the proteins. And we know that myelin is what is attacked in multiple sclerosis. And what is so surprising and still partly not understood is why the peripheral nerves are entirely spared in multiple sclerosis. It's just the myelin in the brain. So it must be something in the Schwann cell that is not attacked, but is present on the oligodendrocyte that is attacked. What you can see from this cartoon is that these cells also work a little differently. The Schwann cell has the life of Riley. It doesn't work very hard. A Schwann cell just makes one wrap of myelin on one nerve cell, whereas the oligodendrocyte has so much work to do. It's sending out processes, and it's wrapping around 15 axons. It's doing a lot of work, and as it gets older, it fades. It can't keep up with the energy demands. This is what the cells really look like. And you can see the oligodendrocyte doing all this work, sending its processes, and the black here is the myelin. So, work by Dr. Trapp, Dr. Lassman, and others has taught us that in MS lesions, the oligodendrocytes are really there. In fact, there are more oligodendrocytes in MS plaques, especially early on after an attack, than there were before. But they're suspended in adolescence. They look like youngsters, and they don't make myelin. So they're just sitting there watching TV. Why aren't they remyelinating? And when they remyelinate, why are they remyelinating so poorly? Well, great information in the last couple of years gives great hope for repair. There are 3 proteins made by genes that are actively blocking, inhibiting repair. And by inhibiting the inhibitors, we can make the oligodendrocytes grow up and make myelin. We are on the threshold of launching the first trial to see if we can repair one of these inhibitors, something called no-go that you might have heard about. I have 20 minutes left, I'm told. It's also now possible to grow oligodendrocytes and show that they can make myelin around plastic wires. So this has made it possible to have wonderful assays where we can screen drugs for inhibitors of the inhibitors. I think the prospects for repair of demyelination and also the hope that this will help people who already have progressive MS or who already have disability is very striking and important. What does the inflammation in MS look like? I'm going to show you now a slide of an MS brain that has been taken at a section just about where our ears are. Left is right and right is left, and that black in the middle is called the ventricle. It's the very top of the lake in the middle of the brain. And I'm going to put it on a loop so that you can see how MS flares up. And most of the flare-up in early MS is below the surface. People feel, oh, I'm not thinking clearly, I'm fatigued, but they're not having attacks. So there's a flare about every 6 weeks in someone with new MS, but an attack that we recognize only about once every 9 months. And that's why MRI is so much more sensitive than how we feel. These white spots are the MS scars. This is a person with multiple sclerosis over a 5-year period so that you can see how these flares develop. It's like rheumatoid arthritis that is flaring in an elbow and then a wrist and then the other knee. And you can see it's on a loop. See in the back here? Let me just show you how it is. A spot here, a spot here, a spot here. One more time. How is this happening? Well, when people look at the tissue, there is a pathology that is fairly unique. And what we see, I showed you that myelin before, and the myelin is black on electron micrographs, so here's normal myelin. This used to be myelin. It exploded and was reformed as little bubbles. That's called vesicular demyelination, and the nerve, which is this thing here that should be in the middle, was pushed to the side. And always, always, right here is a cell of inflammation, a cell called a macrophage or a microglial cell. And that's why you may hear the word macrophage-mediated demyelination. And one of the great triumphs of experimental medicine in the last decade was for the first time being able to replicate this exact pathology in animal models. And what that taught us was really very striking. That you cannot make this pathology just by T cells. You've heard a lot about T cells. But T cells and humoral immune system, meaning B lymphocytes, which make a chemical called antibody that fights infection, are required. This set us to focus on B cells as possible culprits in multiple sclerosis. And I want to be sure I have time at the end, so I'm going to go a little faster now and tell you that on the afternoon, on a Friday afternoon in late September in 2006, we unblinded a trial of the first B-cell therapy in multiple sclerosis. And what we wanted to do was stop those white flares from happening. And here are the white flares on the vertical axis, and on the horizontal axis is a one-year study in people who were treated with a B-cell depleting drug, a drug that kills B cells only in the blood, not in other parts of the body, called Rituxan. One treatment, and then we follow them for a year. And what you see, the black was the placebo, and the blue was the Rituxan-treated group. Disease activity stopped by 91%. The study was then, and it was almost immediate. This is why medicine and science have to come together, because now we can say to the physicians, the physicians can say to the scientists, the B cells are a central culprit. Let's go back and figure out which B cells. This is a Genentech drug. Genentech was bought by Roche. They developed a Rituxan-like drug that instead of being an old-fashioned chimeric antibody that's part mouse, part human, is a fully human antibody, which is better for chronic use. That drug is called ocrelizumab. And without going into details, 92% effective. The phase 3 trials, are any people here in the phase 3 ocrelizumab trials? No, they are underway. 1,600 patients. Another trial in progressive MS will be finished in 2013, and we'll have the answers in 2014. There's no question this will be extremely effective. The only question is, will it be safe enough to use all the time or some of the time? I'm going to speed up and skip this beautiful cartoon that shows you how this happens. Now, everyone here knows about oligoclonal bands, right? Yeah. Those are antibodies. They're antibodies made by B cells through a cell called a plasma cell. It's part of the B cell lineage. What we've learned from studies of the brain and the spinal fluid is that the oligoclonal bands are being made by B cells that are being turned on in the brain. And the same B cells are turned on in the brain and in the spinal fluid, and they're making the oligoclonal bands. We don't know why they're being turned on, but we all have more than 10 million different B cells, but only a few are being turned on. That's what oligo means, just a few. It's now possible, using the same molecular genetic technologies, to ask which B cells are being turned on in the brain. And here is a picture of families of B cells with the parent in the middle and the children all out at the edge. And hundreds of thousands of B cells can be studied in a very quick way using modern technologies from a single person. And when we look together at spinal fluid and brain and blood, what we see is that the B cells that are turned on flow into the bloodstream. And in other people with MS, the B cells are turned on in the in the blood and then move into the brain and cause trouble. The beauty of this is that it's now possible to ask which are the culprits. We can find those in the spinal fluid, track them in the blood, and let's kill them selectively. And instead of killing 10 million different populations of B cells, let's just kill the one that's the culprit here and leave the rest of the immune system healthy. This is the kind of magic bullet that we've dreamed about for 100 years, but now may be possible. All right. I'm going to try to be on time here. Where do we stand? I was introduced a few months back by somebody in internal medicine who said that the greatest advances in modern medicine in the last decade have been in AIDS and multiple sclerosis. I think that's true. And I think it's because of the advocacy and the support of the MS Society. When I started my career, we had nothing. Those of you who have gray hair remember those days. And it's easy to think of the glass as half empty, but I think we also have to be very gratified that at least it's beginning to fill. Where are we? Well, we now have about 10 marketed drugs. And the pipeline in late-phase clinical research, mid-phase clinical research, and early clinical research is just so rich. There's nothing like it in medicine. In 2013, I fully expect that this wonderful medicine, BG12, which looks to be the safest of the effective MS drugs, may be FDA approved. This is a medicine called fumarate that has been a dietary supplement for a very long time. In 2013, there is this toxic but extremely effective drug called Campath, which is a transplantation drug, and it's going to be called Lemtrada when it is launched next year, that is now going to be available. And then we expect the first B-cell therapy, ocrelizumab, to be approved in 2014. So we're beginning to have a very complicated clinical decision-making problem. What drugs for what people, right? We have the older drugs, the interferons and Copaxone, which, looking at this, I've tried to summarize this, how effective the drugs are and how safe they are. These drugs are very safe, but they're not all that effective. They're a little bit effective. Novantrone, some of you may have had Novantrone. It's a chemotherapy drug. It's not safe at all, but it's effective. It has a 1% very serious risk. Tysabri, of course, very important, very, very effective. It's high up, but Tysabri has a risk of this viral infection called PML, which makes it less safe. These new drugs, fingolimod, less safe than we originally thought, mostly because of the cardiac problems, but clearly more effective than interferon or Copaxone. And this brand new medicine that you might have heard about, just FDA approved last week, teriflunomide. And then what's on the horizon? Well, this extremely effective drug, Lemtrada, which is like a chemotherapy drug, a bone marrow transplant drug, BG12 that is effective and very, very safe, and an oral drug, as is fingolimod, and then ocrelizumab. And Rituxan, well, let me, before saying that, say, as you know, we now can make Tysabri very safe for people who don't have blood evidence that they've been exposed to the virus that causes PML. And it's less safe in people who have this virus. So we're often testing for the virus before we use Tysabri, certainly for more than a year. And then we expect both ocrelizumab and maybe also Rituxan to be a drug used in the future. And as we're thinking about this, the goal should be to stop those spots completely, not 90%, 100% as early as possible. If a first-line safe therapy works, we begin with that. And that's an interferon, maybe BG12, maybe teriflunomide, because those are orals. If that doesn't work, a second-line therapy, Tysabri, maybe ocrelizumab, maybe fingolimod or Gilenya, and then the more dangerous drugs as a third line. And I think this is where we are moving. Now I'm going to try something. Do you have nobody? You can tap now. You have an option? I'm getting worried signals here that I have 10 minutes. I'm going to try to show you something cool that is so new that I don't know that it'll work, but it'll be fun to try it. What do we want to do? We want to know, for a youngster, 17 years old, first attack of optic neuritis, what to do. We need to predict the future and understand how different approaches will affect the future. And we can't do that with very short clinical trials that test just one medicine. We need to make MS care precise and personal. And that information needs to be shared back with individuals. And patients need to make decisions along with physicians. Some people just want to delegate decision-making responsibility, but many people want to participate. And we all feel differently about a 1 in 1,000 risk of a terrible outcome from a drug that is far more likely to be extremely helpful. And our wishes need to be heard. But at the same time, we have to know the data, and we currently don't have a way to be able to say, should we start with Tysabri, or should we start with Copaxone? And what we need to do is bring together all of this magnificent imaging, genetic, and other data to let us personalize therapy for people. So I'm going to show you how we are approaching this problem. And this is part of a project that has just been funded through a new federal organization called PCORI, which has as its purpose returning data to people so that we can all make decisions about our health. And this is on an iPad that our physicians have in the clinic, in the research clinic, and that, I'm sorry, and that we are sharing with our patients. So let me see if I can make this work. I'm an optimist. Can I get some audio-visual help? I wish my boys were here. Might have to go to. No. It's on. Terrific. Bingo! 8 years ago, we began a study of 600 people with new onset multiple sclerosis. And we endeavored to follow these wonderful people who have become our partners in research every year with very deep imaging, genetics, other kinds of molecular studies, as well as clinical studies, to try to begin to redefine the rules of the road. Thanks to some very brilliant young physicians and physician scientists who are all supported by the National MS Society, they have now taught me how to think about creating software that can actually be iPad applicable, that is living on the cloud, in the cloud. I'm calling it up live, and and I'm delighted to share this with you. And if the internet works, this will work. So here are patients. You can see their names. Am I violating confidentiality? Nope. Everything is scrambled. The names aren't real. The ages are, and all the medical data is real. Let's go to Anna Santana. Instead of a medical record, this is what the physician has on an iPad. And the beauty about a tablet is that you actually look at each other. You're not looking at the computer keyboard. Electronic medical records are wonderful, but they're just as clumsy as paper records. And what you get out is what you put in. What we've tried to do is design for multiple sclerosis the right things to put in. And it appears on a screen that has clinical imaging and all the molecular information together, along with support tools so that our patients can understand what these mean. And I'll just show you some highlights of this. You've all heard of EDSS, is that right? Yes, so this is a scoring system of MS-related impairments. The higher the score, the worse the impairment. In 2004, you can see when we started, this patient had an EDSS of a little over 3. That meant that she was beginning to have difficulty walking. She could walk okay, but running was becoming impaired. Over the year, you see that she's gotten worse, and she's just about reached the point where she needs a cane. These triangles here show the relapses that she's had over this period, and you see she's had 7. So I'm showing you someone with a very active course. We were treating her, of course, along the way. First with Copaxone and Solumedrol, steroids, but that didn't stop the attacks. You can see in the black, that was the duration of treatment. The attacks didn't stop. She then had a very serious attack in 2006, and we started Tysabri. She responded nicely. We stopped Tysabri because she was antibody positive. Then she had 2 severe attacks, and we restarted the Tysabri. So she had a rocky course. What about compared with other people? Well, we can compare her to all other women approximately her age who have had MS for this amount of time. And that's in the red. And you can see this line, that dark line. Can you all see that? That's what the average person was, and 25% and 75% are the shaded line. She has done worse than her peers. And for us and our patients, we can adjust the demographics for comparison however we like. We also want to be able to use images in a useful way that's really available at the bedside, because this is really our blood glucose equivalent. So we have automated sequences that can analyze the images electronically and compare one to the other. There are many, many kinds of images that we might want to look at, but let me just show you one. Let's look at axials. Let's go a little bit higher in the brain. You've now looked at brains a lot. And do you see there up on the left, which is really the front, that white spot in the center? Do you all see that? Okay, so that is her recent MRI. And let me show you how this has changed over years. So that was not there originally. So in 2000, let me just show you this way, 2004, 5, 6, 7, 8, 9, etc. We can look at myelin. And you can see that she's lost myelin in that spot. Myelin is blue. Let's go back to a quad view. And for those of you who don't know anatomy, we can actually look at the brain in any way that we like, right? And up at the top, it will tell us where we are in the brain. So if we're interested in the in where the right arm and leg nerve cells are, it will tell us there. It will tell us. So it's a very good way to begin to learn anatomy. It also will integrate all of the data at the bedside for our patients. This is the brain atrophy analysis that is so important as MS becomes progressive. And what you can see here, let me make it simpler for you. Our patient has developed about 5% brain shrinkage over this time, which is much more than the reference population. These are all of the genes that she's inherited, and we can ask what the patterns of each of these genes are in different individuals. For her family, we can also show her where her genetic risk is compared with others. And you can see that blue line. She has more of the MS genes than others. And in the next phase of this project that I hope will be ready early next year, the data can all be integrated so that it doesn't end in 2012. It projects to 2017. We're going to do a 5-year prediction. And then one can see, based on other people who are similar, how that prediction changes based upon decisions that we make in 2012. So I think this is the beginning of the future. Precise, personalized medicine for people with MS. Again, this could not have happened without the help of the Society for all of the great young people who are working nationally to make this kind of dream reality for all of us. Deep thanks.